the coat sleeve, it is able to attract small pieces of paper, straw, lint, light feathers, etc. So if we have a glass rod and we rub it with a silk cloth, or we have an ebonite rod, we rub it with a woolen cloth, then it will be able to attract small pieces of paper, feather, or very light objects like our hair. So now the property of rubbed substances due to which they attract light objects is called electricity. So this property due to which uh, these objects like glass rod, like ebonite rod, they attract these light objects. This property is known as electricity. This property is known as electricity. The electricity developed by rubbing or friction is called frictional or static electricity. So this type of electricity which is developed by rubbing things, this is known as frictional electricity or static electricity. Static means where the charges are at rest. So this is that type of electricity where the charges remain at rest. Okay. Now uh, the rubbed substances which show this property of attraction are said to have become electrified or electrically charged. These rubbed substances, like we have this pen and I rub it with my t-shirt, and I try to attract some small pieces of paper or my hair, then this pen is said to be electrified, or this pen is said to attain or gain an electric charge. Okay. Now, what is an electric charge? So our first topic is electric charge. Electric charge. The detailed notes are with you, and here in this class we will make short notes of the theory topics, and derivation I will do completely here, and the numericals also we will do here. All right. Electric.
So you write whatever like you're writing on the
Yeah. Whatever I write here on the board, you have to write it there also, and try to sit on a chair and table. Okay. So electric charge is an intrinsic property. Intrinsic property, the property which is inbuilt, Electric charge is an intrinsic property of elementary particles of matter, which gives rise to electric force between various objects. Electric charge is a scalar quantity. Its SI unit is coulomb. A proton has a positive charge plus E, and an electron has a negative charge minus E, where E is equal to 1.6 into 10 ki power minus 19 coulomb. uh, Electric charge, what is this electric charge? Electric charge is an intrinsic property. It means that intrinsic means it is an inbuilt property which remains inside the materials, and those materials attract small pieces of very light objects. So this is an intrinsic property, means inbuilt property. This is a scalar quantity, and its SI unit is coulomb. Its SI unit, it is an intrinsic property of materials. It is an intrinsic property of materials. Next, it is a scalar quantity. It is a scalar quantity. Next, its SI unit is coulombs. Coulombs. Spelling is COULOMBS. Coulombs. In short, we write it C only. In short, we write the unit of charge as C. Okay. Example. For example, we have protons. Protons are positively charged. We have electrons. Electrons are negatively charged. Charge on a proton or charge on an electron, they have equal charge. Proton as well as electron, they have equal charge, and charge on a proton or on an electron is represented by small e. Small e is equal to 1.6 into 10 to the power minus 19 coulomb. 1.6 into 10 to the power minus 19 coulomb. Okay. We denote charge by small q, by small q or capital Q. Every term is denoted by every term is denoted by some letter, like current is denoted by I, like voltage is denoted by V. Similarly, charge is denoted by Q. Now, next point is electrostatics. Electrostatics is the study of charges at rest. When charges remain at rest, then that type of study is known as electrostatics. Next, let's move to page number 2. Applications of electrostatics. This is a theoretical concept. This is a theoretical topic, and directly for the last, I think, 10 to 12 years, I have been watching that this topic is not directly asked in the exam papers. So, application of electrostatics, we will see it from the top only. Some of the applications are in electrostatic loudspeakers. Second, in electrostatic spraying of paints and powder coating. Third, in fly ash collection in chimneys. Fourth, in a Xerox copying machine. Fifth, in the design of a cathode ray tube used in television and radar. So you have to just read these applications. No need to learn them. Okay. Now, next topic it is two kinds of electric charges. We know that there are two types of charges. First point is there are only two kinds of electric charges, positive and negative. There are only two kinds of electric charges, positive and negative. Second, we know that like charges repel each other, and unlike charges attract each other. The charges are of two types. Charges are of two types, positive and negative. Like charges repel each other, and unlike charges attract. Like charges repel each other, and unlike charges attract each other. Next topic is this clear? Till now, is every point is clear?
Yeah.
Okay.
Yeah.
Next is conductors and insulators. You might be aware of conductors and insulators. Conductors are those substances through which electric charges can flow very easily, through which electricity can flow easily, and insulators are those substances which restrict the path of electricity. Okay, conductors, those substances through which electric charges can flow easily are called conductors. Metals, human, animal bodies, graphite, acids, alkalis, etc. They all are conductors. Next, we have insulators. Insulators, the substances through which electric charges cannot flow easily are called insulators. Most of the non-metals like glass, diamond, plastic, nylon, etc., they are insulators. So I think these 2 points might be very clear to you. Insulators which do not allow electric charges to flow through them, and conductors which allow all the electric charges to flow through them very easily. Next, come to page number 3. Now it is the next topic is electrostatic induction. Electrostatic induction. Induction means to induce something which I have in anyone else. This is called induction. So what is electrostatic induction means? If any object has some charges, then if that object transfer those charges to some other object, then this process is called electrostatic induction. Listen, it is the phenomena of temporary electrification of a conductor in which opposite charges appear at its closer end and similar charges appear at its farther end in the presence of a nearby charged body. It is a phenomena wherein opposite charges comes near the nearer end and similar charges goes to the farther end. Let us understand it through this diagram which is given. Electrostatic induction. So in this, Electrostatic induction. Positively, positively charged glass rod. This one is conducting rod. Conducting rod. This end is A. This end is called B. Minus, 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 minus. It means if a glass rod is positively charged and we bring it near a conducting rod, we have not connected it with the conducting rod is just kept near it, then all the negative charges will try to catch up with these positive charges, try to get attracted towards these positive charges, and all the positive charges which are present in this conducting rod, all the positive charges will accumulate. Accumulate means to collect at some place, will accumulate at this point B. Means opposite charges comes near the nearer end and similar charges goes to the further end. This phenomena is called electrostatic induction. Is it clear?
Yeah.
Okay. Now let's move on to the next topic, basic properties of electric charge. So basic properties basic properties of electric charge. Basic properties of electric charge. It is observed from experiments that electric charge has following three basic properties. Through repeated experiments, it has been observed that electric charge has basic three properties. First property is additivity. First property is additivity. Additivity. First property is additivity. Additivity of electric charge means that the total charge of a system is the algebraic sum of all the individual charges located at different points inside the system. If a system contains charges Q1, Q2, Q3 till Qn, then its total charge is the sum of all the charges. Now look, if I have a little box, and in that box there are so many charges like Q1, Q2, Q3, Q4, there are so many charges till Qn, then the total charge on the system, the total charge of the system Q will be equal to sum of all these charges Q1 plus Q2 plus Q3 dot 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 till Qn. The total charge, the net charge or total charge is the algebraic sum. All right. Now let's move on to page number 4 of the notes. Second property of the charge is quantization of electric charge. First one is additivity. Second is quantization. Quantization of electric charge. Quantization of electric charge. Now, what is this? Quantization means charge is always quantified. Quantified means it can be easily counted. One charge, two charge, three charge, four charge, five charge, like this. We should not say that there are 3.7 charges. There are 7.8 charges. So charges are always quantified. So what does this mean? The experimental fact that electric charges occur in discrete amounts. What is the discrete amount? Discrete amount is this: if we have some books, then we can easily count the number of those books, and the number will be the number of those books will be a positive integer only. Like if we have 7 books, if we have 8 books, we have 9 books, we have 10 books, we do not have 10.1 books, we do not have 10.7 books. So the same phenomena, the same funda is applied on charges also. Charges always occur in discrete amounts. Okay. So instead of continuous amounts, and this is called quantization of electric charge. I am reading point property number 2 on page number 4 of the notes. The quantization of electric charge means that the total charge Q of a body is always an integral multiple of a basic quantum means packet, basic quantum of charge. That is, Q is equal to N multiplied by E, N into E, where N is equal to 0 plus minus 1 plus minus 2, like this. Okay, so E is called a basic charge, and the basic charge, the value of this basic charge is 1.6 into 10 ki power minus 19, 1.6 into 10 ki power minus 19 coulomb. And N is how many charges we have. If we have 18 charges, then the total charge will be 18 into E. If we have 20 charges, then the total charge will be 20 into E. I think that this point is clear to you. Is this point clear to you? Okay. Now there is one question. We will discuss this question. If a body gives out 10 to the power 9 electrons every second, how much time is required to get a total charge of 1 coulomb from it? Okay. Let's move on to the next slide. If a body gives out 10 to the power 9 electrons every second, how much time is required to get a total charge of 1 coulomb from it? We have a body, and that body gives out 10 to the power 9 electrons every second. Okay. So how much time is required to get a total charge of 1 coulomb from it? So number of electrons which the body gives in 1 second is 10 to the power 9. 10 to the power 9. It means that charge which the body gives in 1 second is, okay, the body in 1 second the body gives 10 to the power 9 electrons, 10 to the power 9 electrons, and we know that charge on 1 electron is 1.6 into 10 ki power minus 19. So charge which the body gives in 1 second, the body gives 10 to the power 9 electrons. 1 electron has a charge of 1.6 into 10 ki power minus 19. So 10 to the power 9 electrons will have a charge of 10 to the power 9 into 1.6 into 10 ki power minus 19 coulomb. This is what? This is N. N means number of electrons. This is what? This is E. So this property we have just read. We have just read this property that Q is equal to Ne. E is the charge on one electron and N is the number of electrons. So what is given in this question? That in 1 second a body gives out 10 to the power 9 electrons. 1 electron's charge is 1.6 into 10 to the power minus 19. We simply multiply both of them and then we will get the total charge which is given out in 1 second. Is it clear to you? And whenever we multiply two terms which have some power, then powers get added. So 1.6 multiplied by 10 to the power 9 minus 19, 10 to the power 9 minus 19. So 1.6 multiplied by 10 to the power minus 10 coulomb. Got it? Is it clear?
Yeah.
Okay. Now they are asking how much time is required to get a total charge of 1 coulomb from it. Total charge of 1 coulomb from it. How much time? Whenever something is asked to calculate, we generally keep that thing onto the right hand side of an equation. Like if someone says cost of 5 toffees, I will correlate this concept with this concept. If someone says that cost of 5 toffees is equal to rupees 10, then you tell me what will be the cost of 1 toffee. If cost of 5 toffees is rupees 10, then what will be the cost of 1 toffee? Tell me. Huh? Cost of 5 toffees, price of 5 toffees is rupees 10. Then what will be the cost of 1 toffee?
10 divided by 5.
Yes, 10 divided by 5. 10 divided by 5. The cost of 1 toffee is 10 divided by 5. 5 twos are 10. That is rupees 2. This is cost of 1 toffee. So for calculating the cost of 1 toffee, that means unit, 1 means unit. What you have done? You have simply taken this term and take it to the denominator of this right hand side. The same thing we will do here. In this, they are asking that 1 coulomb of charge, how much time is required? So we have calculated cost here, so we have put cost onto the right hand side. So here we want to calculate time, so we will put time onto the right hand side. So we will reverse this equation. We will say 1.6 into 10 ki power minus 10 coulomb. 1.6 into 10 to the power minus 10 coulomb is the charge that flows in 1 second, is the charge that flows in 1 second. So 1 coulomb charge will flow in what? This term will go in denominator of 1. Are you getting it?
Yeah.
So 1 coulomb charge flows in 1 upon 1.6 into 10 to the power minus 10 seconds. Okay, like this 5 went here in the denominator. In the same way, this 1.6 into 10 to the power minus 10 went to the denominator of this. Okay, now do you know that 10 to the power minus 10 is written in the denominator? If we wish to take to the numerator, then it will become 10 to the power plus 10. Huh? Okay.
Yeah.
Okay. 1 multiplied by, take this 10 to the power minus 10 to the numerator. 1 multiplied by 10 to the power 10. upon 1.6. Now, if we remove this decimal from here, then how many digits are there after the decimal? One digit. Then we will write 10 here. Now, 10, okay, take one power from here also. It will become 100 into 10 to the power 9. What I have done here, is it clear to you?
Yeah.
We have taken 110 from here. So what will remain here? Here 10 to the power 9 will remain here. And 10 into 10 is 100. Why I have taken it? Because I want to divide this 100 from 16. Because 10 will not get divided by 16. So 16 ones are 16. 16 6 are 96. 100 minus 96 is 4. 4. After the decimal we put a 0. 4 0 40. 16 twos are 32. 40 minus 32 is 8. 8 0 80. 16 fives are 80. So 6.25 into 10 to the power 9 seconds is the time in which 1 coulomb charge flows. Alright. So this is the answer of this question, and they have converted this answer to years by dividing it by 365. First of all, they divided it by 24. 24, if they have divided this second by 3600. By dividing it by 3600, it will get converted into hours. If they divide it by 24, it will get converted into days. If they divide it by 365, it will get converted into years. But we are not supposed to calculate it in years. Second is the SI unit of time. So here is the answer. All right. Okay. Okay, Anusha, give me 2 minutes. I'm coming. I'm just going to drink some water. So far we have done two properties of electric charge. First was additivity, second was quantization, and this numerical was based on quantization of charge. Now, third property of electric charge is conservation of charge. Third property is conservation Third property is conservation of charge. What is this? The law of conservation of charge states that the total charge of an isolated system remains constant. Isolated system means a system which is not disturbed or which is not affected by the presence of some other systems. Alright, so the total charge of an isolated system remains constant. Next, page number 5. Second, the electric charges can neither be created nor destroyed. They can only be transferred from one body to another. Electric charges can neither be created nor destroyed. They can simply be transferred from one body to another. Next topic is electric charge versus mass. So conservation of charge means total charge of an isolated system remains constant remains constant. Next point, electric charges can neither be created nor destroyed. Neither be created nor destroyed. Nor destroyed. They can only be transferred from one body to another. The electric charge can be only transferred from one body to another body. All right. Next point is electric charge versus mass. So these were the three properties, three basic properties of electric charges. Next is electric charge versus mass. Electric charge versus mass. So electric charge and mass. This is a theoretical topic. So I will tell you orally what is the difference between electric charge and mass. And if something is required to write, then I will write it. All right. Now electric charge. Electric charge, first of all, the first point of electric charge may be positive, negative or zero. Electric charge may be positive, negative or zero. We know that electric charge can be positive, negative or zero. Now the first point of mass is mass of a body is always positive. We know that mass of a body will not exist if its mass is zero. And moreover, any body cannot have a negative mass. Second point, electric charge is always quantized. Q is equal to NE. Electric charge is always quantized, means we can count the quantity. It will not be in decimals. It is always quantized. But mass of a body, in quantization of mass is not yet established. Quantization of mass is not yet established. If we measure our mass on a weighing machine, then our mass will not come as a round figure quantity. It will come in decimals also. Okay, like 71.1, like 72.2, like this. Third, charge on a body does not depend on its speed. Charge on a body does not depend on its speed. Third point of mass is mass of a body increases with its speed. Okay, all these 3 points are clear to you? Anusha, all these 3 points are clear?
Sir, yeah.
Okay.
Yeah.
Okay. Now, let's move on to the fourth point. Charge is strictly conserved. Charge is strictly conserved means charge cannot be created nor destroyed. Okay, do you know that the third point, mass of a body increases with its speed? How? There is a relation between energy and mass. Energy and mass. What is this energy? Energy also depends upon velocity, means speed. Energy is mainly, if normally we are asking about energy of anything which can move, then we are talking about kinetic energy. So energy is based on mass. So velocity or energy increases, then mass of the body also increases. This happens actually in space. Okay. Now, fourth, charge is strictly conserved. Charge is strictly conserved. We cannot create charge, we cannot destroy charge. It can be simply transferred from one body to another body. Now, fourth point of mass. Mass is not conserved by itself, as some of the mass may get changed into energy or vice versa. Some mass can be converted into energy or some energy may be converted into mass. By this relation, this is called Einstein's mass energy equivalence. So by this relation, we can say that some mass can get converted into energy or some energy can get converted into mass. Fifth point is electrostatic forces between two charges may be attractive or repulsive. Electrostatic forces between two charges. So if there are two similar charges, then they will repel each other. If there are two unlike charges, then they will attract each other. So electrostatic forces between two charges may be attractive or may be repulsive. And fifth point in the mass is gravitational forces between two masses are always attractive. So gravitational force between two masses are always attractive. So two bodies, this is called universal law of gravitation. So two bodies in this universe always attract each other. The force of attraction may be very small or very large, it depends. Okay. Now, sixth point is electrostatic forces between different charges may cancel out. Electrostatic forces between different charges, it may cancel out. Some force may be positive, some force may be negative, because force is a vector quantity. So force may be positive, force may be negative. Then if we add them, then they can cancel out. Positive will cancel the negative ones. Okay. And sixth point in mass is gravitational forces between different bodies. This point I have written, point number 6. It is actually it is not right. Gravitational forces between different bodies may not cancel out. May cancel out. This is wrong. Okay, understand? Because gravitational forces are always positive. So if we add them, then they will not cancel out. Understand, Amisha? Clear?
Yeah.
Okay. Seventh point, a charged body always possesses some mass. A charged body always possesses some mass. We know that. And seventh point in the mass, a body possessing mass may not have any charge. A body which has some mass may be a neutral body also. So, if a body has some mass, it may or may not have charge. But if a body have charge, if a body has charge, then it will have some mass also. Okay, so these were the 7 points. Sometimes sometimes they ask in CBSE exam. Sometimes they ask, keep point out the difference between electrostatic this uh, electric charge and mass. Point out the difference. So you may learn any 4 or 5 points. Okay, all 7 points are not required. Now, next topic is effect of speed on mass and electric charge. Effect of speed on mass and electric charge. Effect of speed on mass and electric charge. According to the special theory of relativity, the mass of a body increases with its speed. In accordance with the relation m is equal to special theory of relativity. As per the special theory of relativity, there is a relation uh, m is equal to m naught upon under root 1 minus v square upon c square, where m naught is rest mass of the body, m naught is rest mass of body, c is speed of light, m is mass of body when moving with speed v. Mass of body when moving with speed v. As v is less than c, thus m is greater than m naught. I will explain these 2 points. First of all, according to the special theory of relativity, you have to learn this relation. According to the special theory of relativity, m is equal to m naught upon under root 1 minus v square upon c square. Now, what is m naught? M naught is called rest mass of the body. What is this rest mass? Whenever we find out, whenever we measure our mass on a weighing machine, then that mass is called rest mass, because at that time we are standing like this on a weighing machine, and we are in a position of rest. We are not moving, we are not under motion. So m naught is rest mass. So whenever we calculate, whenever we measure mass of an object, then that mass is called rest mass of that object. Then what is v? V is velocity of that object. V is velocity of that object. And what is c? C is speed of light. So it is very much clear that none of the object can move faster than the speed of light. So v is always less than c. V is always less than c. And since v is less than c, now I will prove it. V is less than c, then m is equal to m naught upon under root v square minus c square. Sorry, if I take LCM in the denominator, if I take LCM, then c square will get multiplied by this 1. So c square minus v square upon c square. C square. Speed of light is a very huge quantity. Speed of light is a very huge quantity, and the square of that is again a very huge quantity. So if if we subtract anything from the c square, then obviously this will be a positive quantity. Divided by c square, and divided by c square, it means that divided by c square, it means that it will be a again very small quantity. So c square minus v square is greater than 0, positive, and c square is also greater than 0. These quantities both are greater than 0. Then what will happen? A positive term divided by a positive term. C square minus v square is positive, because c square is greater than v square. So if we subtract a small value from a big value, then we get a positive value. C square minus v square is positive, upon c square is also positive. Positive divided by positive is a positive quantity, and when we divide something, when I divide m naught by a positive quantity, then obviously m naught will get divided, means m naught will get reduced. It means that m is greater than m naught. M is greater than m naught. It means that if we measure mass of an object at rest, that is always less than the mass of an object which is in motion. Do you get it?
Yeah.
Clear? Okay. Now let's move on to the next topic. This much is sufficient in this topic. Let's move on to the next topic. It is Coulomb's law of electric force. This is not a derivational part. It is simply an observatory thing. What Coulomb has observed. So Coulomb's law of electric force. Do you want to note anything here?
Huh?
Do you want to note? Do you want to note from here anything? Do you want to note here?
I've already read it.
Okay, okay. Now I am moving to the next slide. Coulomb's law of electric force. Coulomb's law of electric force. So Coulomb's law states that the force of attraction or repulsion between two stationary point charges is first directly proportional to the product of the magnitudes of the two charges, and second inversely proportional to the square of the distances between them. This force acts along the line joining the two charges. So what Coulomb's law states, that if there is a charge q1 here and a charge q2 here, and the distance between these two charges is r, then Coulomb find out that F is directly proportional to the product of the two charges. F is directly proportional to the product of the two charges, and F is inversely proportional to the square of the distance between them. Square of the distance between them. If we combine both these factors, then what we will see, combining these two factors, F is directly proportional to Q1 Q2 upon R square. F is directly proportional to Q1 Q2 upon R square. Okay, now to remove this proportionality sign and insert an equality sign, we always put a proportionality constant here. So F is equal to K Q1 Q2 upon R square, where K, now I am on page number 7, where K is a constant of proportionality called electrostatic force constant for the two charges located in free space. And in SI units we have, whenever the two charges are located in free space, means in air, whenever the two charges are located in free space, then we take this constant K is equal to 1 upon 4 pi epsilon naught. What is the value of 1 upon 4 pi epsilon naught? Its value is 9 into 10 to the power 9 Newton meter square per Coulomb square. So what is the value of this K? This is a proportionality constant. It is 9 into 10 to the power 9 Newton meter square per Coulomb square. Acha, here what is this epsilon naught? Epsilon naught is permittivity of free space. Permittivity of free space. Actually, it also has a unit. It also has a value. Its value is 8.854 into 10 to the power minus 12. But that is not required. It is not asked in question. Okay, so permittivity of free space. What is this permittivity? Permittivity means free space. How much free space permits the charges to flow through them. Okay, this is called permittivity. Permittivity means permission. Okay, epsilon naught is called permittivity of free space. So Coulomb's law can be expressed as Coulomb's law can be expressed as Coulomb's law is, you can write this, F is equal to 1 upon 4 pi epsilon naught multiplied by Q1 Q2 upon R square. This is Coulomb's law of electric force. Okay, is this clear? Anusha, is this clear?
Yeah, yeah.
Hmm? Okay, so today we will do till here only, and the next topic we will start from next class will be on Saturday, na?
Yes.
Okay, so we will do it on Saturday. Okay, Anusha. Until then, you have to learn all these topics. All the notes which you have written, you have to learn them. Detailed notes are not required. You don't need to learn the detailed notes. You need to learn these things which I have written here. All right. Okay, and I can ask anything. I can ask anything in the next class before starting. So you have to learn this. Okay. Okay, Anusha. Bye bye.
Thanks.
Okay.